Again, just a reminder when you're using this, if you use the time links in the description, you can skip right to the problems you'd like to look at rather than watching the whole thing through or skipping around yourself. To get into question number one, this is version A. Question number one, you're given these six diagrams and you're being asked to rank the total resistance. So, which of these is the greatest resistance or the hardest to get through, and which is the least, so which would be the easiest for an electron to get through. Um, we could talk about it conceptually, real quick. Conceptually, when you have resistors in series, it tends to increase the resistance of the circuit because you have to go through every resistor, so it becomes more difficult. Whereas when you add resistors in parallel, such as here, going from 2 to 3, since you still only have to go through one resistor, you're actually adding pathways for the electron, not necessarily resistors it has to go through, and that tends to drop the resistance. Mathematically, this might help some of you. You are told here that I believe each battery and resistor are identical. So we know that the batteries are all the same, the resistors have the same value, so we can make some values up. So that's what I've done right here. So we have A through F. So all I've done is I've just shown that this has two in series. So for A in series, I add those up I total them by adding them up. Now I've decided to make the resistors 2 ohms in each case. So for the first case here, I have two resistors in series. That will give me a total of 4. In the second case, I have two in parallel, so I add them up, but I have to add up the inverses and take the inverse of that. So that gives me 1. And then I continue the same thing through. For C, I add all 3 of them to get 6. In D, I have to add all 3 of them, raising it to the -1. So in this case, that's what I did, and I got a very low resistance of 0.67, so on and so forth. So when I've done that for each one, the resistors in parallel, I use the inverse formula, and the resistors in series, I just add up. We can then see here on the bottom, I've just ranked them. So C is the highest because it's 3 in series, so it's a total resistance of 6 with my made up values. B and F are equal with 1. And then A and E are equal with, okay, so this is wrong. So this is C followed by A and E, and then followed by B and F. And then D is last because D has the least amount. So I apologize, this should read C is greater than A, which equals E, which is greater than B, which equals F, which is greater than D. So these should be flipped with these. If I didn't make a mistake, then am I really being myself? So anyway, version B, you would technically just flip it around because version B is asking you to rank the current. So everything would be flipped because the lowest resistance would be the highest current. So again, this is wrong. It should really say D is greater than B, which equals F, which is greater than A, which equals E, which is greater than C. So everything should just kind of be flipped here. It should be the opposite of version A. If you just make up values for a lot of these problems, you can probably verify or solve quite a few of them. So if you have the time, making up some values might be helpful in a variety of these situations. For number 2, consider the circuit shown below. So we have 3 resistors. They are 1 ohm, 2 ohm, and 3 ohm. The only thing that's changing is the order that they are placed in. So 1, 2, 3, 3, 1, 2, 2, 3, 1. The bulb labeled with an X is the bulb that we want to analyze, and the question says rank the brightness of the bulb. Well, the first thing we need to realize is the batteries are identical, and technically the resistors are also identical. They're in a different order, however, they do have the same value. Now, if we want to know about the brightness, hopefully at this point we realize it has to do with the current. Now, the question here becomes, well, this is a series circuit, so the current's the same. This is also series, and so is this. Now, not every series circuit in the universe will have the same current, but every bulb within one series circuit will have the same brightness. So to figure out which of these has the greatest current, so we can label it here in the greatest box, we have to, again, just do some simple calculations. I don't know what the battery voltage is, but I'm told here that the batteries in the circuit are identical. So in this case, I've just made up a value. So in this case, actually I didn't make up a value, but I could have certainly made up 10. And what we see here is that if I want to find the total resistance in series, I just add them up. So the total resistance of circuit 1 or circuit A is 6, circuit B is also 6, and circuit C is also 6. It doesn't matter what order I add them up in, I get the same total resistance. Now I didn't actually make up a voltage, but I could have. I could have made it anything, 5, 10, 2. If I'm not changing the voltage, because the voltage is the same for every single resistor, every single circuit, and those resistors, no matter the order, add up to the same total resistance, well, if the voltage stays the same and the total resistance is the same, hopefully you realize with Ohm's law, the current in each of these has to be the same. So all three of these are the same, not just because they are all series, because they are all series, have the same voltage, and have the same total resistance. If I had taken this one here and changed it to like 7, that would change things, because if this was a 7, this would now have a higher total resistance than the other two, and the current in this one would actually be slower. So these bulbs would be dimmer. So please just make sure you don't think that every single series circuit will have the same current and the bulbs will have the same brightness like throughout the universe. It's just any individual bulbs within one series circuit cannot be brighter or dimmer than the others. But certainly two different series circuits could have bulbs of different brightnesses. All right, for number 3. Number 3 is a bit tricky. This is one of the things that throws people off the most. And it's when you're analyzing a parallel circuit. So I'm going to first show you a little bit. I'm going to do it mathematically for you here. So again, I've made up some values. So I made up 10 volts as the battery. I made up 2 ohms for each of these. Now the switch here could be open or closed. I am only going to look at what's happening with bulb A here, because that's what the question is asking about. So if we take a look with the switch open, if we assume this is open, so current cannot pass through here, well, then we would only have this one part of the circuit getting electricity. It's only one bulb, so it would get the full 10 volts. So with just this one bulb, meaning this is open, this bulb will get 10 volts. Because if I travel through this pathway, I go through one bulb, it gets all 10. We know the resistance, which I also made up, is 2. So using Ohm's law, I find 5 amps of current will travel through this bulb. Now when I close the switch, that does nothing as far as bulb A is concerned, because yes, I have 2 in parallel, but if I choose this pathway, I still only go through the one bulb at A, so the voltage is still 10, because in a parallel circuit, voltage is the same. The resistance is still 2, so using Ohm's law, I will still find that there's 5 amps traveling through this bulb. If you think about it, the fact that I close or open the switch doesn't change the voltage that this bulb gets. It doesn't change the resistance of the bulb. It can't change the current in there. It's the same reason why if you have a light on in your room, and then you go across the room and you turn on another light, the first one doesn't get dimmer, it doesn't get brighter, it stays the same brightness. You just now have 2 bulbs on in the room, because these 2 branches do not affect one another. It's the same reason why when I open that, this bulb goes off, but this one doesn't. This switch in no way is on a pathway that will affect the bulb at A. Now, what some people might do is if you make up numbers and you combine these using the inverse and then use the 10 volts, you will find that the total current in the circuit actually goes up. When this is closed, there is 10 amps of current coming out of the battery. And why is that? Well, because when this is open, I need 5 amps based on our math to go through here. When I close this switch, well, this still gets the 5 amps because nothing's changed. However, this bulb also gets 10 volts. It also has a resistance of 2, so it also needs 5 amps. So if instead of filling one branch with 5 amps of current, I now need to fill 2, yes, they each individually only get 5. But how can I provide both of them 5? Well, now the battery in this one section and in this section, there must be 10 amps of current. 10 amps come out, it splits. 5 goes here, 5 goes here, and when they come back together, 10 goes back here. So as we've said in a parallel circuit, the current is not always the same everywhere. It splits up, it comes back together. We just have to recognize that yes, the battery will have to kick out more current because now it's actually powering 2 bulbs, but as far as bulb A is concerned, nothing's changed. For number 4, similar to number 3, I have a single circuit with one bulb. I have a second resistor wired in parallel and a third resistor wired in parallel. This little instrument here is called an ammeter, and it just measures the amount of current. So if the current flows faster through this point, the needle will be higher. If it's flowing slower, the needle will be lower. It just gives you an idea of how much current is flowing through a particular point. The question asks us, rank the current measured at that location. So which of these would be the greatest, which would be the least? Is it a trick question? It's all the same, so on and so forth. Before I get into that, I want to show you something that might help you understand this a little bit better. Kind of a weird setup, but let's assume that we had a pipe and there was a lever on top, and if you pumped that lever, you would pump water into this pipe. Now, right here, there's a little gauge. It measures how much water you are physically pumping into the pipe. So as you pump this, this will go up, and then the water will flow out the other side. Kind of a weird setup, but bear with me. If I wanted to pump 10 gallons of water out of this pipe, well, you would have to pump 10 gallons in. Why? Because it's one pipe. So if 10 gallons is coming out, 10 gallons had to go in. There's nowhere else for water to have come in or have gone. Now let's say I decided to add a second kind of pipe on here, and I still want 10 gallons coming out of each. Well, you can no longer just pump 10 gallons into this. If I pump 10 gallons into here, then only 5 gallons will come out of each. If I still want to maintain 10 gallons per pipe, yes, there'll be 10 gallons coming out here. There'll be 10 gallons coming out here. So individually, both of those pipes will individually only have 10. But if I want 10 to come out of two pipes, you now have to pump more water. You have to pump 20 gallons in because each branch or each pipe is now going to get 10. If I added a third and I wanted again 10 gallons, well, now you have to pump enough so that 30 gallons comes in so each one can get 10. Now, these parallel circuits work the same way. While the individual branches might get the same amount of current, we have to recognize that there is a point where the battery has to pump in more current to fill up these branches. So if I try and show you this maybe a little bit more with an actual circuit diagram, when the switch is closed, in this case, kind of going back to what I was talking about in number 3 up here, when the switch is closed, based on my made-up numbers, well, they each get 10 volts, and each has a resistance of 2 ohms. So they both will have 5 amps of current flowing through them. How do I fill two branches with 5 amps each? I have to have 10 amps of current. The 10 amps travels here, splits 5 and 5. Technically, the 5 and 5 come back together over here. As soon as the switch is open, well, bulb 1 still gets 10. It still has a resistance of 2 ohms. Therefore, Ohm's law tells me it will get 5 amps. Now, when there's only one bulb, it's 5 amps everywhere. This is basically a series circuit. But as soon as I close that, the one battery is now no longer powering one thing, it's powering two. So we have to recognize that with the parallel circuits, the first and the last portion of the circuit typically will have more current because you need to pump enough current in that first and last branch to fill up all the other branches. If I individually look at a branch, yes, I will have a lower amount. Just like if 10 people left, I don't know, one building, and they went to another building, but there were two pathways, I know there will be 10 people here. I know there will be 10 people. I don't know necessarily how many people will be on each, but I do know that at the starting and ending pathway, I have to have all of the people. They could certainly split between hallways, but the beginning and ending path have to have the same number of people as I started with because there's nowhere else for them to go. If we look at number 5, I'm just going to explain this one using this visual. I haven't written anything out on the answer key. So we're given some current here, and we're asked first to rank the voltage at locations A through H. So we know we spend voltage when we go through a resistor. So if I assume that this is the direction of the current, which is not conventional current, this is actually what's really happening. The electrons are moving. Well, an electron leaves here, and by the time it gets to A, it has gone through 0 resistors, so it has the maximum amount of voltage. If I continue, I technically still have the maximum amount all the way through this path. Now, right when I hit this point, I cannot go any further without going through a resistor. That's like being on a highway, and you cannot go any further until you pay a toll. You're not paying money. The electron is actually losing some energy as it goes through here, and that energy gets converted into whatever this resistor converts it into. If it's a light bulb, it converts it to light. If it's a stereo or a speaker, it converts it to sound, so on and so forth. Now, once I go through that resistor and I wind up at point B, I must have less voltage than A because I have gone through a resistor. You will notice that to get to point B from the battery, I must go through one resistor. To get to point C, I must go through one resistor. To get to point D, again, one resistor. So B, C, and D are actually all equal. Those are 3 locations in which you have spent the voltage on one resistor. So A is the greatest. It is greater than B, which equals C, which equals D. Now, in order to get to the next section, I must go through a resistor. So one way to look at it is, if I were to start over, to get to point G, I must go through 2 resistors. To get to point F, I must go through 2 resistors. Even if I chose this pathway, to get to F, I have to go through 2. So A is the greatest. I've gone through no resistors. C, B, and D are equal because to get to any of those locations, I've gone through 1. To get to F or G, I have to go through 2. And no matter what I choose over here, I have to go through a third one to get to H. So your final answer should be A is greater than B, which equals C and equals D. That's greater than F, which equals G, and that's greater than H. At H, you have 0 volts. You have no more resistors to go through, so you get back to the battery with 0 volts. Now, the current is a little bit trickier, but here's the things I'm looking for when I give you this type of problem. We first have to recognize the fact that the current has no choice but to go through A. There's one pathway. Even though there's a resistor, the current must all go through point B. There's no other option. My first option comes when I can make a decision here. And we'll talk about this in a second. After I make this decision, you'll notice everything comes back together and must go through G. Then a decision can be made, and then everything has to go through H. So because there is a single pathway at A, B, G, and H, those are the 4 singular pathways which will get all of the current. So your final answer for the current ranking must begin with A equals B equals G equals H. If I were to cut the pathway that A, B, G, or H is on, at any point, the circuit would entirely shut down because every electron has to go through those pathways. If I cut it right here, these 2 resistors would no longer work, but I still have a functional pathway for everything else. So A, B, G, and H are the maximum current because all of the current goes through those points. If we look at it now, I think even though the current goes this way, I'm going to explain it from the other way because it's a little bit easier without doing the math. The current down here will have 3 different pathways you can choose from. I mean, even technically up here, it's a little more complicated to understand, but even up here, it's got 1, 2, 3 different pathways. So each of those pathways will get 1/3 of whatever current goes through, and that's because we know the resistors are identical. So an electron that hits here says I can go through this one, or I can go through this one, or I can go through this one, and an electron basically says to itself, well, they all cost the same, I don't really care which way I go. So 1/3 will go here, 1/3 will go in this section, and 1/3 will go here. Now, that means that C is equal to D because they both get 1/3. And since D is on the same branch, the same pathway as F, that means that F and D have to be equal. Whatever passes through D must pass through F. So to recap for the current, A equals B equals G equals H because they get all the current. But those 4 points, you will have more, so the current is greater than at C, which equals D, which equals F. If we take a look at number 6 here we have 3 diagrams. Now if we ignore this wire in the middle, we basically see that these are 3 identical circuits that have 3 light bulbs and the same battery. All batteries, all bulbs are identical. So what happened here was somebody came along and they wired a second wire, and they short circuited some of these bulbs. So in the first case, if I'm an electron, I leave the negative side. I now have 2 choices. I can go through 2 resistors and get to the point where I'm closer to the end, or I can jump right past them through this free pathway with no resistance and continue on my way. Just like if you wanted to go out on the weekend and your parents said you can do these 2 chores or you can just go, you're not going to choose to do 2 chores. You're just going to take the path of least resistance. So what I've done in each of these cases, I'll explain really quickly, and then I'll show you the visual. So at this point, these bulbs get nothing. At this point, the electron will go here, bypass those 2, and only travel through bulb X, which is the only one here. In the second case, it has to go through the first bulb, but when it hits this point, it will never choose to go through 2 resistors when it can zip down this free pathway and get to the positive terminal, which is where that electron wants to be. And likewise at the end, it must go through the first bulb. I can completely bypass the second, and then I have to go through the third. All right, so what I've done here is I've redrawn. That's a lie. There we go. It's a little bit out of order, but I've redrawn each of these. So just to show you, I can cut out this entire section because nothing goes through it. So I get this weird kind of lopsided circuit like this. In the second case, these 2 are effectively useless because they don't get any current because of that short circuiting. So it looks like that. And the third one, the only thing I'm cutting out is that middle bulb. So really, from an electron's point of view, these are what the circuits look like. Now the question is asking, rank the voltage drop, meaning how many volts are spent or how many volts are lost going through these circuits. So I just have to recognize for point X in each of these. So if I look at the diagrams I've drawn, in this case, there is only one bulb. One bulb, in order for me to get back with 0 volts, gets the full voltage. So if this is 10 volts, we'll make that up. Bulb X gets all 10. There's nothing else to share it with. In the case of B, you'll notice that bulb X actually is in the section that doesn't even get any current. So it will literally get 0 volts. It gets no voltage because it's not even a part of that circuit as far as that electron's concerned. And in the third case, yes, X is in this circuit, but it also is in series with another bulb, meaning that I have to split my voltage. If we assume everything's identical in this case, they will both get half. So if we look at these circuits and you understand why I drew them the way I did, and we recognize that we were looking at bulb X, A must be the greatest because literally bulb X gets all of the voltage. C is the middle because I have to split it. So whatever that voltage of the battery is, if it's 10, I'm only getting 5 because the other 5 is getting spent going through this bulb. And in case B, X isn't even in the circuit, so I get no voltage. So it's full voltage, half voltage, no voltage. So your final answer should be A, C, B. You definitely should be able to get B because X is not even in that circuit. Then you just have to recognize case A, 1 bulb, don't have to share anything. Case C, 2 bulbs, so I have to get about half of that voltage for each of those light bulbs. Number 7, anytime you're asked to draw a diagram, I think the easiest way would be to follow the example I'm going to give you right now. It's kind of a little bit drawn out. It doesn't necessarily need to be, okay, lovely, it's out of order again. All right, bear with me. Number 7. So one of the things that I would highly recommend for those that are having trouble with this is we need to recognize that since I have 3 rooms here, and houses are wired in parallel because we don't want these rooms to affect one another. So whatever's happening in room 1 should not affect room 2, so on should not affect room 3. So one of the first things you should get in the habit of doing is drawing your battery source and just drawing a long line at the top and a long line at the bottom, and then put little tiny lines for room 1. So room 1 is whatever is going to happen in here. Room 2 will happen in here, and room 3 will happen in here. If you draw this first, based on how many rooms you have, you now know because of these little lines that room 1 is completely separate than the other 2. Whatever I do in here, an electron can bypass that and go to room 2. It can bypass room 1 and 2 and go to room 3. So any of these things will be separate from one another. All right, maybe you don't need this much detail, but I'm going to give it to you anyway. So if we look at room number 1, it has 3 light bulbs. All 3 lights can be controlled by individual switches. That immediately tells me if I can control them individually, they do not affect one another. That should scream out to you, parallel. When things don't affect one another, they must be wired in parallel. So the next thing I do is I just literally split that into 3 pathways. So I've now split that into 3 pathways since I know they need to be independent. I know I have to have a bulb on each of those, and I know they have to be controlled by switches. So after splitting it into 3 pathways, I put my switch, I put my bulbs. Still not a complete circuit, but at least now I've taken care of the fact that they cannot affect one another. If I open this, it's not going to affect these other 2. This one gets a little bit tricky because 2 of the 3 lights can be controlled by a 4th switch that does not affect the other. So one of the things we have to do is take a step back and say, well, if 2 of these now have to be separate from the other one, well, right now all 3 of them are separate from one another. But if I want these 2 to be together but separate from that, hopefully you realize I need to connect these. I could be the first 2 or the second 2, but I now need to, lovely, I now need to connect them. So I've now connected these 2, and then hopefully realize, well, if I add a switch on this pathway, I can take a step back and say, well, this switch will kill that one, this one will kill this one, this will kill this one. All 3 are individually controlled. If I open this, both of these will go out without affecting this one. So it's kind of a little trial by error, a little bit of critical thinking. Room number 2, 2 bulbs and a refrigerator. The refrigerator can never be shut off, no matter what, and the light bulbs can be controlled by 1 switch. So I'm going to wait right there, and I'm going to take a look and say the refrigerator can't be shut off, but the light bulbs can. So if 1 bulb burns out, the other will shut off as well. So if 1 bulb burns out and the other shuts off, that immediately tells me it's series. So I have light bulbs in a series pathway, and I have a refrigerator in a pathway by itself. If I don't want these to affect one another, that screams out to you parallel. First thing you do, split that second room into 2 branches because we have to keep these things separate. All right, so the next thing we need to look at is going to be the light bulbs can be controlled by 1 switch, and if 1 bulb burns out, the other will shut off. And the refrigerator needs to be separate. So what I've decided is in one of my pathways, I've added a refrigerator, and in the second pathway, I have my switch and my 2 bulbs. If the switch opens, the light bulbs burn out. If I remove one of these light bulbs, it's in series, the other light bulb will go out. So it's a little bit of trial and error. Get in the habit of recognizing when things don't affect one another. You need to split them into separate pathways. Room number 3, I believe I did all in one shot. 4 light bulbs, each can be controlled with a switch that immediately should scream out to you, parallel, I need 4 branches. 2 of the 4 can be controlled at the same time, and the other 2 can also be controlled. So I immediately need 4 branches. So I split that into 1, 2, 3, 4. Each branch gets its own switch and light bulb. That takes care of everything being controlled by a switch. Going back to what we did in the first case, if I need these 2 to be separate than these, I need to connect them, add a switch, that'll control that. If I need these 2 to be separate than that, then I connect them, add a switch. So the types of questions you'll be asked like this, you don't necessarily have to think in this many steps, but I find it's a little bit easier to go step by step, figuring out when you should be splitting branches, when you should be combining them. For the last 3, which are the mathematical problems, at this point, hopefully you've been exposed to a variety and feel comfortable with this. But just to show you, if I can find it, number 8. First thing we should always do is add up our total resistance. This is a series circuit, so we simply add them up. 6 and 4 is 10 plus 3. My total resistance is 13. Then, when I know the voltage is 30, which was given, and I've now found the total resistance of 13, I can use Ohm's law and divide 30 by 13 to get my total current of 2.3. We need to recognize conceptually that in a series circuit, the current is the same, so that 2.3 can be listed everywhere. And then using Ohm's law, V equals IR, I multiply I and R, and I will get my voltage that is spent at each of those, the voltage drop across those resistors. If I'd like to double check, I trace any one pathway. Well, I only have one here. I have to go through 3 resistors. So in this case, if I add up my 3 voltages, because I have to go through all 3, it should add up to 30, and I'm pretty close here. A little bit of rounding throws it off, but I get very, very close. So that's a way that I can know immediately that there's like a 99% chance I did this correctly. If we look at number 9 is the parallel version. So for the parallel version, it's a very similar process, different equation. I need to calculate the total resistance. So if I have an 8, a 3, and a 9 in parallel, I have to add them up using the inverse formula. So inverse of each, add them up, take the inverse of that. So I get a final total resistance of about 1.76. I'm given that the voltage is 23, so I have my total voltage, I have the total resistance of 1.76. Ohm's law tells me, therefore, that the current in this circuit coming out of the battery is 13.097. I can use Ohm's law with the given voltage and the, never mind, I just did that, it's late, I apologize. In a parallel circuit, the voltage is what's the same, not the current. So I can take the 23, list it everywhere, and use Ohm's law, V equals I times R. 23 divided by 8 gives me 2.875, so on and so forth. Now these 3 do not add up to the total down here of 23, but remember, any one pathway has to add up. So if I go through the 8 ohm resistor, I've gone through 1, I get all 23. If I go through the 3, 1 resistor, it gets all 23, and so does the 9. So if I double check, it costs me 23 volts to go through any pathway, which is what I'm looking for. For number 10, this is a complex circuit, a little bit trickier. We start with the same basic idea. We need to find the total resistance. For the total resistance, I have to recognize that I have 3 in parallel and then 3 that are in series. So 99% of the time, you'll start with your parallel branches. So if I add up the 5 to the -1, the 4 to the -1, if I combine those 3 using the parallel formula, and then I recognize that I have to use then the series formula, which is just adding these, I combine everything in parallel, and then I simply add that result to the 6 plus the 2 plus the 3. 3 in parallel, 3 in series. That combines for total resistance of 11.67. I know the voltage is 42. I just found my total resistance. So I can plug it into the table and find that the current coming out of the battery is 3.59. That means 3.59 leaves the battery. There is no choice but for all 3.59 to go through the 6. So the 6 ohm resistor gets the full 3.59. The current will then split based on these pathways, but afterwards it will come back together, which means the 3.59 amps has no choice but to go through the 3 and the 2, because this pathway and this pathway, every electron has to go through, all the current has to go through. There's a choice here, no choice here or here. So the 6, the 3, the 2, 632, they should get the full 3.59. To then figure out what's going on over here, we have to use Kirchhoff's rule. So if I come down here, I have just copied over this section you see here. Now we know 3.59 amps of current is what's coming into this branch because we know that that's what's coming out of the battery. So we have 3.59 coming in, and I have a 5, a 4, and a 1. So what Kirchhoff's rule tells us is you represent the current in the largest branch with an X. Then you just set up a proportion. 5 divided by 4 is 1.25. So there's 1.25 more current in this branch. Pretty close because it's only slightly less. 5 divided by 1 gives me 5. This is 5 times less resistive, 5 times easier to get through. So we'll have 5 times as many electrons, 5 times the current traveling through. Still don't know what X equals, but if 3.59 went in, when I add the current in this branch to this branch and this branch, it has to add up to 3.59 because that's the amount of amps or amperes that filled this in. So I know that the current in this one, which is 5x plus 1.25x plus x, I'm just adding up the currents, has to equal the total that went in. I can then find my total for x of 0.495, and since that's the one in the 5 ohm branch, the 5 ohm branch of the 3.59 gets 0.495. To find what the 4 ohm branch gets, I take that number, 0.495, I multiply it by 1.25 to get my 0.62. Close, but a little bit more because it's a little less resistive. And then the 1, I take this number and multiply it by 5, and I get my value of 2.48. V equals IR. I can now multiply I times R for each of them and get my final voltages. Again, if I add all of this up, I will not get 42. However, I don't go through all 6 resistors. If I look at this question, at maximum I go through 1, 2, 3, 4, or 1, 2, 3, 4, or 1, 2, 3, 4. Any 4 that I go through must add up, and you'll notice the 5, the 4, and the 1 all cost the same amount. So these are the 3, the 21, the 10.77, the 7.18. These are the 3 that I must go through. And it doesn't matter which of these pathways I choose because they each are only going to add 2.48. So if I add up 1, 2, 3, and 4, or 1, 2, 3, and 4, or 1, 2, 3, and 4, depending on whether I choose the 5, the 4, and the 1, those will always add up to 42. And that's how you can know that you've done a complex circuit correctly.